In the last class, we looked at how scattering takes place due to various particles. Today, we look at examples of scattering that you can see in everyday life. That is, you go outdoors and you see a number of phenomena, essentially optical, which owe their origin to scattering. The best example, of course, is rainbow. All of you have seen rainbows, but I am not sure how many of you have looked at rainbows at the fundamental level and try to understand what factors control the occurrence of primary rainbow and then the secondary rainbow and even higher level rainbows. Okay. So, today we will try to look at this phenomena and see whether we can understand them from scattering perspective. The first slide here shows the rainbow over Potala Palace in Tibet, a very impressive picture with very detailed resolution of the various colors. But there are other examples also now we will look at. Now, in all this phenomena, there is scattering from a sphere. Okay. And in the last class, we saw that scattering has various features in it. The first is reflection, that is like ray A, that is the difference in refractive index of the liquid drop, water drop and the surrounding air causes the reflection of this ray A. Then the second one is refraction, that is ray B. It comes here, gets refracted once at this interface, goes inside, gets totally inter-reflected, comes back and refracts out. And you will see this is an important phenomena in rainbows. Then you see ray C, which is diffracted, which goes close to the raindrop, but does not quite touch it, but anyway bends on account of diffraction phenomena. And ray D is refracted once, reflected twice and then again refracted. And then ray E is refracted, reflected once and refracted. Okay. So, all these have some role to play in your rainbow. Now, here is a rainbow, the primary rainbow and the second rainbow. This is second rainbow, the primary rainbow, and you see a clear distance between them, which is called the Alexander's dark band. That is where the reflection is rather low. And also notice that the color sequence in the two rainbows is not the same. In the first rainbow, the red color occurs on the outside. In the second rainbow, the red color occurs on the inside. So, the question you should be able to answer is whether we can explain these features of the rainbow, the distance between rainbows and the color sequence being reversed, can it be explained through understanding of the basic phenomena of scattering. Here is another picture here, which shows again the primary and the second rainbow, and notice the second rainbow is much more faint than the primary. So, as you go to higher order scattering, higher order reflection, the intensity gets weaker. So, theories say there are even more rainbows, but most often you do not see them. Many cases you do not see the second rainbow, you only see the primary. secondary already is weak, but there are also tertiary and other rainbows. Here is another picture where the primary rainbow is very clearly visible, and then your dark band, and then the secondary rainbow is somewhat subdued. Here a similar picture with clear difference between primary and secondary rainbows. Now, although you may not have seen it very often, you can also get completely circular rainbows. That depends on at what distance from the droplets you are. So, if we are at the right distance, then you will see the entire rainbow circular one in front of you. Here is a picture taken in Hawaii, showing the complete circular rainbow with a secondary rainbow also visible. As a matter of fact, the best way to understand a rainbow is either to computer simulations, or as what Dr. Murthy has done in his website www.armchair.com. He shows how you can set up a simple experiments in your house to observe rainbows. All you need is a spherical glass container which admits sunlight from outside in, and on reflection on the wall you can get many kinds of rainbows. So, the simple geometric optics of the rainbow says that the ray coming in has to bend, and depending on this angle it can get totally in turn reflected and then refract out. So, for you to see the rainbow, the sun has to be behind you, and the angles have to be such that the ray on refraction undergoes total internal reflection until it goes out on this side. If the angles are not right, it may just refract out, and so the angles are very important in this observation of rainbows. And best way to see is that the human observer has to make an angle of 40 degrees with the sun's rays coming towards the droplets. Now, the rainbow owes its existence not only to the occurrence of refraction and total internal reflection, it also is due to dispersion. What is dispersion? Dispersion is a phenomenon which occurs because the refractive index of water varies with wavelength. For example, the refractive index of water at the red wavelength is 1.330, while at the violet wavelength it is 1.342. Difference of 0.01 has enough impact to create the rainbow. And the angular spread of sunlight is about 0.5 degrees. The sun is not exactly parallel, and this smaller than the spread of scattering for plane wave light, which was here 1 point. So, the colors can be expected to be seen distinctly. So, although it is not quite parallel, it is sufficiently parallel for you to be able to see clearly the rainbow. So, according to this, the primary rainbow should have a width of 2.23 degrees, which is very close to observation. Now, here is a more clear picture of the primary rainbow phenomena. You can see that the red and blue light of the sunlight come here, and after refraction, reflection and refraction, because of the slight difference in the refractive index, the ray, the blue and rather the violet and the red rays come out at slightly different angles. Okay. And so, this is the angle that 40 degrees that we saw in the other picture. So, if you look at the ray parallel here and after refraction, internal refraction and other refraction, the angle is 40 degrees, and that angle is slightly different for the violet and the red in the VIBGYOR spectrum. So, this is similar to what you observed in the laboratory in your physics lab, when you send in white light to a prism, red and blue come out because of the difference in refractive index, and the same thing is happening here. The red light undergoes a change in angle of 40 degrees, while the violet light only undergoes change of 40 degrees. Now, you saw the secondary rainbow in those pictures. What is the secondary rainbow due to? That is when the rays are incident and after refraction, instead of one reflection, they are in a position to undergo two reflections, two internal reflections, and come out, and they come out at a different angle. And notice that in contrast to the primary rainbow, where the violet light appears above the red light, here in the second rainbow, the violet light comes below the red light. That is why the two rainbows are in inverted sequence. As you saw in the one rainbow, red was outer and blue was inner, the other one was the other way around, and this is because of the way it underwent reflection. In one case, there was only one total internal reflection, while in the other case there were two reflections. And this is another picture clearly identifying the geometry of the problem and showing the total bending by 42 degrees for the red light, and for the blue or the violet it is around 40 degrees. So, this is essentially same, there is no difference between this and the previous one. So, this is again illustration of the two rainbow phenomena and how the change in angle occurs. So, here the second rainbow geometry again shown with two refractions and two internal reflections. Now, the best way to understand the rainbow phenomena is to look at the intensity of scattered light as a function of the scattering angle. Okay. And in this calculation done by solving the full electromagnetic equation, Maxwell's equations, what is being shown is the scattering intensity in relative terms for liquid droplets, water droplets of various sizes, starting from 0.1 micron, 1 micron, 10 micron, 100 micron, 1000 microns. This is from a wonderful website called www.philipavon.com, which discusses many optical phenomena in that website. And what you see is that when the cloud droplets is very, very small, it is not raining cloud, but merely a small cloud droplet, the intensity of scattering is small and is not varying much with angle. As you go to higher and higher radius of the droplets, the intensity goes up almost a million times from 0.1 to 1, and you start seeing some variations in the scattered intensity. And as you go to 10 micron, you start seeing very large changes, and what you see at the scattering angle of 0 is called corona, the high scattering here, and the high scattering here is called glory, and we will look into this little later. And then you go to 100 micron, there is the yellow one, and finally 1000 micron, which is the most important dimension, because that is where you get actual raindrop. These are cloud drops, these are small in size, they will never actually fall to the ground, because their settling velocity based on Stokes law is very, very slow, and hence they will never reach the ground as droplets, they will evaporate. Only droplets of the size of 1000 micron are in a position to retain their enough mass to fall on the ground. So, look at 1000 micron, you can see that the intensity of scattered light is about million times larger than that of, let us say, 1 micron cloud drop. So, cloud drops will not give you rainbow, only raindrops will give you. Okay. And you see clearly the primary and secondary rainbow occurring at angles here measured with respect to the forward direction. That is why you are getting angles like 140 instead of 42, because that 40 degrees you saw in the earlier picture, here you should look it up on as 180 minus 42. So, 138, that is the primary rainbow, and the other one is 50 degrees or 130 degrees. So, these two rainbows show a sharp increase in intensity. So, you are able to see them distinctly in the sky, because there is more scattering into this angle than any other angle here. So, locally there are the maxima which you are able to see very distinctly. There are of course, other maxima which is not shown in this picture, which refers to tertiary and higher order rainbows. And in between you see the sharp drop in scattering, and that is the dark band, Alexander dark band. And you notice that this is not there in the lower size liquid droplets. So, liquid droplets must be at least 100 micron and above for this feature to emerge. So, whenever you see a rainbow in which you see a primary and secondary along the Alexander dark band, you can be sure that it is raining somewhere, because these droplets are large enough to cause rainfall. Now, the same thing now is shown in a polar diagram, and this is the size parameter 2 pi r by lambda, and you can clearly see that there is backward scattering here, forward scattering here, which leads to phenomena such as corona and glory. And only when its size becomes very large, of the order of 10,000, that is 1000 micron size particle at the value of around 0.7 micron. So, you can see that only when the size parameter is around 10,000, you see a distinct high scattering around the primary and secondary feature, about 42 degrees and 50 degrees from this side is backward scattering. That the sun has to be behind you for you to see the rainbow. So, what you see is that we are in a position to explain a natural phenomena such as primary and secondary rainbow as well as the dark band from applying the basic laws of electromagnetic theory, Maxwell's equation, solve them on the computer, and every observed feature can be explained by the phenomena of what is called Mie scattering. That is scattering in which the particle dimensions are much larger than the wavelength of light. In this case, we are talking about visible light, so 0.4 to 0.7 micron, while the size of the raindrop is of the order of 1000 microns. So, you see a ratio of the order of 10,000 here, which is necessary to get this. If you have only say 30, you will get glory and corona, but you will not get the distinct rainbow structures. Now, the best way to show this is by computation. So, here you see a clear explanation, I think taken from the website I had mentioned earlier. If you put a 10 micron liquid particle, you will not see any distinct color, you will see a diffuse scattering, and it will become sharper and sharper as the radius of the liquid droplet increases. And then you start seeing the dispersion, and finally, when it comes to about 500 micron, you see distinct primary rainbow, secondary rainbow. So, all this is from theoretical calculations clearly demonstrating that for very small droplets the rainbow is colorless, you will not see a real rainbow and is not well defined, and as the droplet size starts increasing, you start seeing this black regions which are really the Alexander dark band, and only when the size reaches 500 micron you see a clear rainbow structure, and so this can be simulated by Mie scattering formula very nicely. Now, recently a paper was published in which people were able to identify the not the secondary, but tertiary and the next one rainbows, and this of course is very faint, but they were able to compare the measured distance of the red, green and blue and so on with the calculated value from Mie scattering, and you can see they are pretty accurate. So, the theory is able to predict the occurrence of the tertiary and higher order rainbows to within 0.5 degrees, which is quite remarkable. And remember that the kind of theory we are proposed here is proposed in these papers published in Applied Optics. They are assuming droplets are all of the same size. Now, you will not expect in the real atmosphere that all the droplets will have same size, there will be distribution of droplets, but droplets which are too small will not give a rainbow, and droplets which are too large would have anyway fallen out. So, only droplets which are large enough to cause rainbow and which have not yet fallen to the ground are contributing to your rainbow. Still the results are truly impressive that the theory and observation in the case of scattering is so well understood. So far we have looked at liquid droplets. The advantage of liquid droplets is that they are spherical in shape most of the time, and only very large droplets lose their shape and become slightly distorted, but most of the time because surface tension they maintain their spherical shape. But when it comes to ice particles which are solid, not liquid, they come in a large number of shapes, hexagons and plates. So, you can see various examples here of ice crystals of regular shape, some of them are irregular shape also. So, these ice particles whose dimensions can be up to 0.2 millimeters will create optical phenomena of a greater variety than the rainbow, because rainbow is produced by spherical particles, water drops, and the only parameter which varies there is the radius of the droplet. If the droplet is very small, we do not see rainbow, and if it is very large, see it, but droplet radius above 1 millimeter or 2 millimeters are very rare because they fall down. So, the range that causes rainbow is fairly narrow, but in the case of ice particles, you see a huge plates and bullets and all kinds of shapes are there. So, you should expect that ice crystals will produce scattering phenomena called halos, and so you should see a number of these phenomena. Now, many of you in India may not have seen these spectacular effects of ice particles, because they are not that common in India, but both in the Arctic and Antarctic, those who have gone for exploring the polar region, they do find huge number of phenomena involving scattering of sunlight and even moonlight, and that is because ice occurs more often in the Antarctic and Arctic conditions, and so these phenomena are seen there more often. Now, here is a picture of scattering, probably scattering with scattering angle for a hexagonal crystal of at wavelength of 830 nanometer, 0.8 micron. You can see that the variation of scattering intensity with scattering angle has only a few features in the front, around 22 degrees and slightly larger angle here 44. And of course, this is the rainbow thing we saw earlier, which is a spherical particle. This is, and you are shown the curves for two different wavelength. Okay. And you can see a rough surface will completely remove this peaks. So, in order for you to see the optical phenomena created by scattering of ice particles, the ice particle have to be smooth and reasonably uniform in size, so that effects of different ice particles do not cancel out. So, this is not commonly observed phenomena. The phenomena that is observed as crystal has been given a lot of nomenclature, so that people can compare and contrast their discoveries. The one you see on the top is called the circumzenith arc, which you see well above the sun, and that is caused by flat ice crystals. And the other one is called the upper tangent arc, that is caused by solid, what you call bullets, and depending upon their orientation, horizontal, vertical, they can cause a 2-degree halo or a perihelic circle or perihelia or sundogs, which you will see later, and the lower tangent arc. So, all these phenomena that are marked here are caused by ice crystals here of different shapes and sizes and orientation. So, remember that the phenomena that you see is linked to the existence of ice crystals of a certain shape and orientation. And also remember that these are rare, because all the ice crystals which are formed must have similar sizes. If the ice crystals formed have a range of sizes, then the phenomena may not be as distinct and you may not be able to see it so clearly. Again, the same picture, but now highlighting the role of 22 and 46 degree angle in the picture, as well as the existence of a large vertical structure here called the sundog, which appears on either side of the sun, and one which appears right above the sun is called sun pillar. So, all these phenomena have been analyzed through scattering by ice particles, and many of them can be explained from first principles. Here is another little picture identifying the same thing. Now, you have to remember these when we look at wave pictures. Remember, the sun pillar occurs above and below the sun, sun dog appears on either side of the sun. Then you have the upper tangent arc and the circumferential arc and the two halos at 22 and 46. So, all this we will. So, halos are a 22-degree radius circular halo centered on the sun and sometimes the moon, often milky white and sometimes colored with a reddish tinge. Okay. So, here is the halo that you see around the sun. So, this is caused by ice crystals. And this is another picture, in spite of the sun being blocked, the halo is still visible. Now, here is the example of a 22-degree halo, most common phenomenon that is observed. Due to ice crystals. Here is a halo observed behind a building, and this is caused by the moon. So, on a full moon night, if there are ice crystals in the sky between you and the moonlight, you will see a moon halo. Again, this angle is 22 degrees, this angle. Now, the best way to explain the 22-degree angle of the sun is that the rays of sun or moon enter the side face of the hexagonal prism and are refracted across the crystal and they come out to the other side. So, they enter through one face and go up another face, and as in the case of rainbow, there is a dispersion. So, you should see some color, but the color is not very strong, and so you may not see it so distinctly, but it is there. Careful photography has revealed there is a rainbow like structure there. And you can see that the difference between the 22-degree halo and the 40-degree halo is essentially with reference to the orientation of the crystal. Okay. In the case of 40 degrees, the ray enters the top of the hexagon and then comes out of the side. So, the geometry here favors the 46-degree halo, while the 22-degree halo we saw is coming from the side of the hexagon and exiting other side. So, whether you see a 22-degree halo or a 46-degree halo will depend upon whether the ice particles falling in the sky, they have to fall because they are heavier than air, whether they fall horizontally or vertically. So, that is the vertical horizontal will determine the kind of halo you see. And this is explained little more distinctly in this picture, in which the 20-degree halo comes in because the rays enter one side of the hexagonal prism and exit to the other side, causing a 20-degree deflection, while the other one enters through the other side, but enters to the edge phase it enters, and here the angle is 40 degrees. So, all these are easy to explain based on laws of refraction. Now, the sun dog is caused by reflection by flat ice crystals, and it is really the two edges of the sun which are reflected through the crystal as shown here, and your eye, when it extrapolates backwards, it sees the sun dog appearing on either side of the sun. Actually, it is coming from the edge of the sun, but due to refraction it is deflected slightly. So, for the observer, this light coming in and on reflection entering here, we extrapolate backwards and we see it here, and the other one we see it there. Okay. So, that is the sun dog. So, this can also be demonstrated in the laboratory as shown in this laboratory picture. So, many of these phenomena can be easily be done at home or at the laboratory, because everything can be done through geometric optics. So, here pointing out that it is clearly visible on full moon, and here you see the halo clearly, and here is the sun dog that is visible. And the sun dog geometry is explained more clearly here. When you have flat crystal, the ray entering to the top and exiting to the side will do a 22-degree change in direction. So, it is caused by hexagonal flat plates, and when the flat plates are falling horizontally in the air, they cause the sundog phenomena. And in Antarctica, this is, so this again you can see clearly here, hook, where the sun has been blocked deliberately. Here you see the sundog, and you see the upper arc that we discussed. So, all these are visible in Antarctica, where ice crystals are plenty throughout the season. The glory, as you saw, is a scattering phenomena. So, this is not so common, very often observed through the flying aircraft. And here is a very nice picture of the pillar near the sun and the two sun dogs, clearly visible as well as the upper arc here. So, this again pictures in the polar region, where ice crystals are quite common. The atmosphere is quite clean and pristine. There is no contamination by aerosols. So, here these phenomena are very well observed. The second most frequent of the halos is the when horizontal size ice particles fall down, and this is a slightly different angle here. It is coming from one side and go to the other side. Previous one came from the top, this is going to the side. So, the side face inclined at 60 degrees. And here is another example of two sun dogs on either side of the sun, and one more picture showing the sun dogs and the sun pillar here. So, the one we saw on the top, called the circumzenithial arc, is a refraction of rays through faces inclined at 90 degrees, these two faces. Produce very pure, well separated prismatic colors seen here, and so this is can be shown to be coming at that angle. And here is a sun pillar reflected on a water body after sunset. So, that is an interesting picture. And here you can see the light rays are reflected by the both upper and lower faces. So, it is coming inside from the side and exiting through the top. So, it is the both internal reflection and the role of the upper lower surfaces here is what is causing the. Now, for astronomers, all these phenomena are very important, because if you are looking at a star overhead, there is no problem, but if when you are looking at the star at an angle, then the apparent position of the star is not same as the actual position, because the rays of the stars are refracted through the sky. So, you have to correct for it. So, these are things which have been studied by astronomers very closely, because they want to know the actual position of the star, not the apparent position here. You know the actual position is here, you have to correct for it by measuring the refraction. Now, refraction is also very important during sunsets, and all of you have watched this. So, when a sun is setting, the rays from the sun actually bend due to changes of refraction index in the atmosphere. So, once more your eye extrapolates backwards. So, even after the sun is set, you see the sun. Okay. So, the sun is set here, but because of the bending of rays, you see the sun as not having set. So, if you want to calculate precisely the sunset time to within a few seconds, then you have to account for this refraction. And this is another way to explain that picture. Now, when the sun sets, you see some very interesting distortion of the spherical shape of the sun, and this is again on account of refraction. And you see a dramatic example of sun setting here, and changes in colors and change in shape of the sunlight. And the most important is the distortion that is there, which we will see is really linked to properties near the horizon. Here is another example of unusual distortions as the sun sets. One of the most intriguing phenomena that is caused by refraction is the green flash. Atmosphere here is behaving like a that is, after the sun is set, there is a detached green flash you will see. And now, this is happening because the refractive index varies with wavelength that we already saw, and when you go to a very low position on the horizon, the depth over which the refraction is occurring is very large. So, the whole sun is bent by angle of 0.6 degrees. So, among the rays that are bending, the red has a least amount of bending, and green and blue have much more bending, and therefore, this green you are seeing really are the rays of the sun after it has set, and those rays having bent much more. So, the green light which you see has started out slightly above the red, and it reaches the eye at a steeper angle because of more bending. Blue also scattered, maybe it is scattered out. Now, this green light is distinctly visible here. Here the green light is visible very, very clear above the sun, and this is the image of the sun that is shot a few seconds earlier, and the rays of the sun were bent by the atmosphere, and it appears above the orange sun. So, the red has less bending due to refraction than the green, and that is coming out. These are rare phenomena, not observed every day, because you need very, very clear skies, no clouds, no rainfall, which can cause distractions. So, it requires a lot of patience to able to photograph these unusual optical phenomena of the sun. Now, here is more detailed explanation. The refractive index of the red light is 1.000292, and refractive index of the blue light is 1.000295, they are different in the 6th decimal place. Still you see a very clear distinct effect of refraction here, with the red and the green separated, well separated by about 0.006 degrees or 20 arc seconds. So, this is really small. Normally, you will not see it because you can resolve only 100 arc seconds, but under special conditions you see this. You also see this flash when bright planets like Venus and Mars, Jupiter are setting. Same logic has to work, but for that you need a telescope. So, astronomers who watch these phenomena with telescope have observed these phenomena quite distinctly. Now, all of you know that the color of the sky is blue. What this curve shows is the observed skylight, this is observed intensity of skylight in the visible region. The thin one is the solar spectrum. To solar spectrum, you will add a Rayleigh scattering law, that is 1 over lambda to the power of 4, you get this. And you can see that it cannot fully explain why the observed maxima in the blue is there. It is more seen in the simple theory as to occur in the violet. So, the blue curve is the model as goes lambda to the power of 4. Orange curve is the sun spectra. So, it clearly shows that due to Rayleigh scattering by molecules, the peak of the reflected scattered radiation occurs closer to violet and blue compared to the sun spectra, which maximizes around green yellow region. The green yellow region, this is violet blue region, and this is the role played by Rayleigh scattering, which scatters more light in this region than this region. So, some of the phenomena like glory and fog bow, which we saw in the scattering signature, can be seen on full moon days. Here is a halo, here is a fog bow. Sometimes you will see doubles and dogs, 1, 2 and there is one more. And the other interesting phenomena that you see is the light reflecting off a lake also undergoes, and this is see the primary rainbow here, second rainbow here and a reflected rainbow. So, this is the sun's ray reflected from the lake, and after reflection and coating raindrops and then causing this third rainbow, whose angle is quite different from the secondary and the primary rainbow. So, all these are easily explained through ray tracing or using Mean scattering formula. Now, one more thing that we can explain from basic theory as to why the sun is white at noon, somewhat yellow in the afternoon, somewhat red in the evening. And essentially at noon, the path through which the rays are travelling is fairly short, but as you go to the afternoon, the path increases, more and more blue radiation is scattered out, that is the blue sky, but the remaining rain coming with the sun is richer in yellow than in blue, because blue is scattered out. And as you go past to the evening, the path length decreases even further here. So, both the blue and the green get scattered out and you see only red. So, the color of the sun you see is based on how much color from the sun is scattered out. The white color of the sun scattered out due to scattering, and that depends on the number of particles in your path. So, on a clear day, this is what you will see, but on a day where there are all kinds of particles in the atmosphere, like man-made aerosols or naturally occurring dust or some other feature, then of course, you can see some very interesting colors of the sun and moon on days when we have, let us say, after a day with huge volcanic eruption, in which a large number of particles are put in the stratosphere, and these particles are reasonably uniform in size, then they can do wonderful scattering phenomena, and you can get a blue colored moon, which is very rare, and that is why it is called, we use the expression once in a blue moon, because that kind of phenomena occurs only when there are major volcanic eruptions, and those eruptions occur once in 20, 30, 40 years. So, these are rare phenomena. Now, with that we have covered the discussion on how scattering controls natural phenomena. Now, we move on to actually quantitative aspects of the phenomenon. This was discussion today was merely qualitative, in which we merely highlighted how we can explain various natural phenomena like rainbow, halo, sun dogs and so on through ray tracing or through maze scattering algorithms, and some of them are quite quantitative, but it is important to know how to calculate the scattering by particles and the net effect of scattering in quantitative terms. So, to do that, we go back to our equation for pure scattering, that is, we neglect emission. If you recall, in the radiative transfer equation, there is a term involving emission, which requires a knowledge of temperature of the medium and its variation. But if the situation in which you are dealing with, the emission is occurring at a very different wavelength than the wavelength of interest to us. Like for example, we are interested in understanding how solar radiation is scattered and reflected by either cloud particles or other particles, then the emission by the medium at wavelength around 10 micron would not interest you, because you are only focusing on, let us say, the visible radiation. So, in such a case, we can solve a pure scattering problem in a more elegant way, and you recall that we had well known two stream approximation, wherein we divided the radiated rays to rays moving upwards and downwards to hemispheres essentially, and we saw that the equation can be written as mu d I plus upward going rays and you have on the other side I plus, and you have the single scattering albedo coming in here. This is one equation for the upward intensity. Similarly, the second equation for the downward intensity, which we had derived earlier. Now, notice that these are two equations in two unknowns, and the two unknowns are I plus and I minus in this case, and these can be solved, and the solution is a straightforward solution of coupled differential equation, and the solution can be written as I plus the upward going ray is equal to C1 e to the power of gamma tau plus C2 e to the power of minus gamma tau, where gamma is a quantity which connects the single scattering albedo and the direction cosine square. So, the decay of the intensity depends on the single scattering albedo as well as the direction it is traveling. We will continue this solution in the next lecture and show how the results obtained from the solution of the equation helps us to interpret the various results that are relevant to both engineering and atmospheric science.